everyone, my name is NORAMIE TALINO, and this morning we are going to tackle the Lesson 8, the analysis, interpretation, and use of test data. But before that, let's have first our learning objectives. So, at the end of the lesson, the student should be able to analyze, interpret, and use of test data applying measures of central tendency, measures of variability, measures of position, and measures of covariability. So what are measures of central tendency? So the word measures of central tendency means the central location or point of a set of values. So there are three commonly used measures of central tendency: the mean, median, and mode. But let's talk first the mean. So when we say mean, this is the most preferred measure of central tendency for use with test scores, also referred to as the arithmetic mean. So when we say mean, we are computing the average. So paano nga ba natin i-compute yung average? So here the formula for mean. This is how we are going to compute the mean. So this is the formula. Mean is equals to the summation of x divided by the n, which is the number of scores in the set. So in table 8.1, it shows here the score of 100 college students in final examination. So the mean is the sum of all scores from 53 down to the last score is 35. So paano nga natin makukuha ang mean? So here is the computation. So we have to follow this. So in traditional is napakahaba yung computation kasi you have to add 53, 36, 57, and so on and so forth hanggang sa makarating sa 35 para makuha natin ang sum of all scores. And bago natin siya i-divide sa the number of scores in the set. So, kapag ni-add natin ang lahat, we have the 4,720. Divide natin sa 100. So, our mean is 47.2. So, ito yung mean natin. So, this is our mean. In table 8.2, frequency distribution of group test score. So, since sa lesson 7 is gidiscuss ni Pudina yung mga class interval, midpoint, frequency, f of x, cumulative frequency, and cumulative percentage. So, this is how we are going to locate or we are going to compute the mean or the average. So, this we are going to use the formula where mean is equals to x of 1, which is the midpoint of the class interval, f is the frequency of each class interval, n is the total frequency. So now, mean is equals to the summation of x, which is 4,720. And the total of frequency is 100. So if we are going to divide it, so the answer will be 47.2. So this is our mean. There is easiest way to compute the mean using the SPSS. So when we say SPSS, it stands for Statistical Package for the Social Sciences, wherein ito yung ginagamit nila para mas mapadali ang pag-compute ng mean. So all you have to do is to follow the following steps. Now let's proceed to the second, which is the median. So when we say median, is the value that divides the rank score into halves or the middle value of the rank score. Now let's proceed to the second, which is the median. So when we say median, is the value that divides the rank score into halves or the middle value of the rank score. Now is we are going to identify or we are going to determine on how to compute the median. So table 8.2, this is the frequency distribution of group test scores. So in order to determine the median, we have to use this formula. So since there are already discusses on how to get the lower limit of median class, size of the class interval, the cumulative frequency, now is we are just only going to substitute. So 44.5 is the lower limit of median class, which is 45 to 49. Now, 5 is the class interval, size of the class interval. Then, n is equals to 100 divided by 2. Then, our cumulative frequency is 62 in the median class, but we are going to use the cumulative frequency below the median class, which is 44. So, ito yun. Then, we have to divide it to the frequency of the median class, which is 18. So, yan siya. So, 100 minus 2 equals to 50. Minus 44 equals to 6. So, just copy the left side, which is 44.5. And you are going to compute it. So, 44.5 plus 5 times 6 divided by 18. So, the median will be 46.17. In order to get the median, so the statistical software can do it easily. So, all you have to do is to follow the step in order for you to get the correct computation for median. And now we're moving to the last one, which is the mode. So when we say mode, it's the easiest measure of central tendency to obtain. So if the scores are arranged in a frequency distribution, the mode is estimated as the midpoint of class interval which has the highest frequency in the set. Using statistical software and following the steps on finding the mean and median, so this image will be appear. So that's the end of my report for today. Thank you for listening, and let's proceed to the next reporter.
Good morning, everyone. My name is JOYNIE TORNALEJO. I am the second reporter of Group 5. Okay, I will be discussing to you what are mean, median, and mode appropriately used. To appreciate comparison of the three measure central tendency, a background of level of measurement is important. Mean is the most frequently used of central tendency and generally considered the best measure of it. There are some situations where either median or mode are preferred. Median is preferred measure of central tendency when, first, there are few extreme scores in the distribution of the data. Second, there are some missing or undetermined value in your data. The third one is there's an open-ended distribution. For example, if you have a data field which measures number of children and your options are 0, 1, 2, 3, 4, 5 or 6 or more than the 6 or more field is open-ended and makes calculating the mean impossible, since we do not know the exact values for this field. The last one is you have data measures on an ordinal scale. Mode is preferred measure when data are measured in a nominal and even sometimes ordinal scale. Okay, let's proceed to scale of measurement. It is a classification that describes the nature of information within the values assigned to variables. Understanding the scale of measurement is important to interpret the numbers assigned to people, objects, and events. There are 4 levels of measurement that apply the treatment of test data. First is nominal measurement. The number is used for labeling or identification purposes only. An example is used for identification number or section number. In data processing, instead of labeling gender as female or male, you can use code 1 to represent a female and 2 to represent male. We know that 2 is greater than 1. In this case, the difference between 1 and 2 has no meaning. Wala dito gina-indicate na ang male is better than female. The purpose of this is to simply differentiate or categorize the subjects by gender. The second one is ordinal level of measurement. This will be used when the value can be ranked in some order to characteristics. Ordinal indicates order. For example, in academic awards from highest honor, high honor, and with honor. Also, rating surveys and restaurants, when a waiter gets a paper or online survey with a question, how satisfied are you with the dining experience? Having a 0 to 10 option, 0 being extremely dissatisfied and 10 being extremely satisfied. The third one is interval level of measurement, which has the properties of both nominal and ordinal. Scales is attained when the values can describe the magnitude of the difference between groups or when the intervals between the numbers are equal. It is the differences between measurements but not through zero. For example, when we measure a temperature in Fahrenheit, the distance from 30 to 40 is same as the distance from 70 to 80. The interval between values is interpretable. The last one is ratio level of measurement. The highest level of measurement. It carries the properties of the nominal, ordinal, and interval scales. For example, if achievement in a performance test in physical education by the number of push-ups one can do in minute or distance run in an hour, or in a typing class where you count the words type in a minute. Okay, now let's proceed to how the measure of central tendency determines skewness. First figure is mean, median, and mood and a symmetrical distribution. It is a normal or no skew. On this perfectly symmetrical distribution, the mean, median, and mood have the same value, and the value of the median is between the mean and mood. Same pa dito ang frequency distribution. So, ang mean, median, and mood ay parehas ng value. The second figure is a mean, median, mood, and a positively skewed distribution. On this positively skewed distribution, the mood stays at the peak and its value will be the smallest. The mean will be pulled out from the peak of the distribution toward the direction of the few high scores. Thus, the mean gets the largest value. The median is between the mood and the mean. Dito sa figure 2, kung ang distribution ay positively skewed, ang mood ay magiging mababa ang value kasi nandun siya sa negative direction. Ang negative direction ay yung sa left side natin. So, ang mean ay magiging mataas ang value kasi nandun siya sa positive direction. Ang positive direction ay yung sa right side natin. Third figure is a mean, median, and mood in a negatively skewed distribution. The mood remains at the peak of the curve, but it will have the largest value. The mean will have the smallest value as influenced by the extremely low score, and the median still lies between the mood and mean. Dito sa figure 3, negatively skewed distribution siya. So, ang curve niya ay nasa negative direction. Ang mood ay may pinakamataas na value kasi nandun siya sa unahan ng positive direction. Ang mean ay may pinakamababang value kasi andun siya sa low scores kahit na nasa positive direction siya. That's all my report. Thank you and God bless. Magandang RMMC.
Hello everyone, good morning. My name is Kristine Ungab and I will continue to discuss the topic. What is coefficient of variation as a measure of relative dispersion? You should remember that the range, semi-interquartile range or quartile deviation, and standard deviations are all expressed in the units of original scores. They are all measures of absolute dispersion. So when we say absolute dispersion, it is the same unit is used in absolute measure of dispersion as in the original data set. The absolute dispersion method expresses variations in terms of the average of observational deviations, such as standard or means deviations. It includes terms like range, standard deviation, quartile deviation, and so on. So for example, one distribution of test scores in mathematics may have a standard deviation of 10, and another distribution of scores in science may have a standard deviation of 5. So if we want to compare the variability of the two distributions, so when we say variability, ito yung kung gaano kalawak na distribute yung scores are in the distribution. That is the amount of the spread of the scores around the mean. So can we say that the distribution with the standard deviation of 10 has twice the variability of the one with standard deviation of 5? So we have another example. One distribution has a standard deviation of 8 meters, while another has a standard deviation of 15 pesos. So can we say that the latter distribution is more spread than the former? Or can we compare standard deviations in meter and pesos? So parang obvious na dito yung sagot because in absolute dispersion, only the same unit is used because we cannot conclude anything by direct comparison of the two absolute dispersion because they are in the different categories such as meter and pesos. So let's go back to our example. One is the mathematics score distribution while the other is the science score distribution. To make comparison logical, we'll need to dimensionless or when we say unit-free measure of relative dispersion. The coefficient of variation is another name for this measure of relative dispersion. So when we say relative dispersion, this is just the ratio of the distribution standard deviation to the distribution mean. So this is the formula that the coefficient variation is a percentage number. CV stands for coefficient variation is equals to standard deviation divided by the population size times 100. Thus, if the average mathematics score of the students is 40 and the standard deviation is 10, the coefficient of variation is calculated as this. Coefficient variation is equals to 10 over 40 times 100 is equals to 0.25 or 25%. Assume that students' average science score is 18 with a standard deviation of 5. The variation coefficient is CV is equals to 5 divided by 18 times 100 is equals to 0.277 or 28%. So, naggamit tayo ng 10 and 5 as the standard deviation of mathematics and science scores. So, dito, we may conclude that the set of mathematics scores is twice as dispersed as the set of scientific scores. So, next, how is standard deviation applied in a normal distribution? The standard deviation is regarded as the most relevant measure of variability since it approximates the percentage of scores that are within 1, 2, or 3 standard deviations from the mean in various distributions of scores, not only in evaluation but also in research. So next, we have the normal distribution. So the normal distribution, this is frequently used to compare scores. So ito yung usually na ginagamit upang mag-compare ng mga scores. So when a frequency polygon for a large distribution of scores of a natural phenomenon and occurring characteristics like IQ, height, income, test scores, etc. These are drawn as smooth curve. One curve are stand out, which is the bell-shaped curve. So as you can see, it has a small percentage of observations on both tails, and on the inner part of this curve are the bigger percentage. So this curve known as the normal curve, it is also called as normal distribution. So this was named after Karl. So this was named after Karl Friedrich Gauss, also called the Gaussian distribution. So this was used as a standard reference for many statistical decisions in the field of research and evaluation. So here, the standard deviation becomes more useful because it is used to determine the percentage of scores that fall within a certain number of standard deviation from the mean. The area in the curve refers to the number of scores that fall within a specific standard deviation from the mean score. There are fixed percentage of each portion under the curve such as 68%. So this is the area under the normal curve, and of the scores fall between 1 standard deviations below and above the mean. 95% of the scores fall between 2 standard deviations below and above the mean. 99.77% of the scores fall between 3 standard deviations below and above the mean. So the following figure further illustrates the theoretical model. So this is the area under the normal curve. So from the example figures, we can state the properties of the normal distribution. 1. The mean, median, and mode are all equal. So equal dito lahat ang mean, median, and mode. 2. The curve is symmetrical. As such, the value in a specific area on the left is equal to the value of its corresponding area on the right. So when we say symmetrical, both sides are the same. 3. The curve changes from concave to convex and approaches the x-axis, but the tails do not touch the horizontal axis. So when we say concave to convex, concave means it was rounded inward, while the convex is rounded outward. And lastly 4, the total area on the curve is equal to 1. And that would be the end of my report. Again, my name is Kristine. Thank you.
Good morning, I am Kristine. So today, I will be going to continue the report. What are standard score? Standard score is the number of standard deviations by which the value of a raw score is above or below the mean value of what is being observed or measured. Raw scores above the mean have positive standard score, while those below the mean have negative standard scores. Z-score. Z-score is a conversion of raw data to a standard score when the conversions is based on the population mean and population standard deviation. There are many kinds of standard score, but the most useful is the Z-score, which is often used to express a raw score in relation to the mean and standard deviation. This relationship is expressed in the following formula. So here's the formula of Z-scores. Z equals X minus X with bar divided by S, or standard score equals observed value minus mean divided by standard deviation. So now let's recall that X minus X with bar is a deviation score. With this difference, we are able to know whether your test scores say X above or below the average score. However, you cannot say whether your test scores or grade is better or worse than the average score. Again, the importance of knowing the standard deviation is to help you to locate the relative positions of the scores in the distribution. In the preceding sections, we discussed raw scores, which are the original scores collected from an actual testing situation. However, there are situations where computing measures from raw score may not be enough. Consider a situation where you, as a student, you want to know in what subjects you perform best and poorest to determine where you need to exert more effort. Or maybe, in the past, you took an entrance examination in more than one university and asked yourself in which university you perform best. In case like this, we cannot find the answer by merely relying on a single score. More concretely, if you get a score of 86 in English and 90 in P6, you cannot conclude that you perform better in P6 than in English, simply because 90 is higher than 86. Say you later learn that the mean score of class in English was 80 and in P6 the mean score was 95. Will your reaction change? This situation indicates that a single score like 86 or 90 is not meaningful unless it is compared with other test scores. In particular, a score can be interpreted more meaningfully if we know the mean and variability of the other scores where that single score belongs. Knowing this, a raw score can be converted into standard scores. Figure 8.8, a comparison of score distribution with difference means and standard deviations. In the above figure, a score of 86 in English indicates better performance than a score of 90 in P6. Let us suppose that standard deviations in English and P6 are 3 and 2 respectively. We can express these raw scores as a Z-scores. For example, ZE as English equals 86 minus 80 divided by 3 equals 2, and ZP or P6 equals 90 minus 95 divided by 2 equals negative 2.5. From the above, if 86 and 90 are your scores in the two subjects, you can confidently say that compared with the rest of your class, you perform better in English than in P6. That is because in English, your performance is 2 standard deviation above the mean, while in P6, your scores is negative 2.5 standard deviations below the mean. While 90 is numerically higher, this scores is more than half standard deviation below the average performance of the class where you belong, while 86 is above the mean and even 2 standard deviations above it. Having been transformed in the same scale, the two graphs can be taken as one standard distribution of scores. Figure 8.9, different row scores in one z-score distribution. So here's examples of z-scores. For example, you get 75 in English and 62 in math. So 75 in English and the mean score is 70 and the standard deviation is 5. So z equals 75 minus 70 divided by 5 equals to 1. Next is math, 62 in math and the mean is 56 and the standard deviation is 3. So z equals 62 minus 56 divided by 3 equals 2. So another example of z-score. So a student obtains a mark of 56 on a test for which a mean mark is 67 and the standard deviation is 10.2. The student's standardized mark is close to A, negative 1.08, B, negative 1.01, C, 1.01, D, 1.08, and E, 49. So the answer is A, negative 1.08. So here's the solution. So Z equals X minus X with bar divided by S equals 56 minus 67 divided by 10.2 equals negative 1.08. So the answer score is A, negative 1.08. And then next we have t-scores. It's a conversion of a raw data to the standard score when the conversion is based on the sample mean and sample standard deviation. So t-scores, as you see in the computation of a z-score, it can give you a negative number, which simply means the score is below the mean. However, communicating negative z-scores as below the mean may not be understandable to others. We will not even say to students that they get a negative z-scores. Z-scores may also be a repeating or non-repeating decimal, which may not be comfortable for others. One option is to convert a z-scores into a t-scores, which is a transformed standard score. To do this, there is scaling in which a mean of 0 in a z-score is transformed into a mean of 50 and the standard deviation in z-score is multiplied by 10. The correlation responding is t-scores equals 50 plus 10z. So, for example, a z-score of negative 2 is equivalent to a t-scores of 30. That is, t-scores equals 50 plus 10 multiplied by negative 2 equals 50 minus 10 equals 30. Looking back at the English score of 86, which result in a z-scores of 2 as shown in figure 8.7, t-scores equivalent is t-scores equals 50 plus 10 multiplied by 2 equals 50 plus 20 equals 70. Examining further figures 8.7 and 8.9, where 7 scores range from negative 4 to positive 4, more than 99% of the scores are between 20 and 80. And next we have stay 9. So another standard score is stay 9. So shortened from standard 9. With 9 in its name, the scores are on a 9-point scale. In a z-score distribution, the mean is 0 and the standard deviation is 1. And we'll see in a figure 8.7 and 8.8. In this scale, the mean is 5 and the standard deviation is 2. Each stay9 is 1/2 standard deviation wide. Like the t-score, stay9 score can be calculated from the z-score by multiplying the z-score by 2 and adding 5. That is, stay9 equals 2z plus 5. Going back to our example on a score of 86 in English, that is equivalent to a z-scores of 2 and a figure 8.9. Its stay9 equivalent is stay9 minus 2 multiplied by 2 plus 5 equals 9. So, example, scores in a stay9 scale have some limitations. So, since they are in a 9-point scale and expressed as a whole number, they are not precise and different z-scores or t-scores may have the same stay9 score equivalent. So, we have the z-scores, t-scores, and stay9. So, the z-scores, we have 2.1, 71, and then 9, 2.1, 70, and then 9, 1.9, 69, and then 9. On the assumption that stay9 scores are normally distributed, the percentage of cases in each band or range of scores in the scale is as follows. So, we have the stay9 score and the percentage of scores. So, 1, we have the lowest, which is the 4%, 2, next low, 7%, 3, next low, 12%, 4, next low, 17%, 5, we have the middle, which is 20%, 6, next high, 17%, 7, next high, 12%, 8, next high, 7%, and 9, we have the highest, which is the 4%. With the above percentage distribution of scores in each stay9, you can directly convert a set of row scores into stay9 scores. Simply arrange the row scores from lowest to highest, and with the percentage of scores in each stay9, you can directly assign the appropriate stay9 score in each row score. On the interpretation of stay9 score, let us say that Kate has a stay9 score of 2. We can see that her score is somewhere at the low or bottom at the 7% of the scores. In the same way, if John's score is in a 6 stay9, it falls between the 77 percentile simply because 60% of the scores are below the 6 and stay9 and 23% of the scores are above the 6 stay9. For qualitative distribution, stay9 scores of 1, 2, and 3 are considered as below average, while the 4, 5, and 6 are average, and the 7 and 8 are above the average. Thus, you can see that your scores of 86 in English is above average. Similarly, Kate's scores is below average, while that of John is average. So, here's are the figure 8.10 that it shows the normal distribution and the standard scores. And that's all for my report. Thank you for listening.
Hello, good morning. My name is Sophia Mayu. I'm gonna report now what are the measuring of core variability. Measuring of core variability, it's describe how much scores are spread out or differ from one another but take into account how similar these different or change are for each person from one variable to the other. Measure of covariability tell us to a certain extent the relationship between two tests or two factors. Admittedly, a score one get may not only be due to a single factor but with other factors directly or indirectly observable which are also related to one another. At the point when we are keen on discovering the level of connection between two scores, we are dealing with the correlation between two factors. In simple terms, covariability is the correlated variation of two or more variables. The statistical measure is the correlation coefficient, an index number that ranges from -1.0 to positive 1.0. Next is the value. 1.0 indicates a negative perfect correlation. Next is 0.00, no correlation at all. Next is 1.00, a perfect positive correlation. There have been many correlation studies conducted in the field of assessment and research, but correlation coefficients did not result in exact value of 0.00 and negative 1.0 and positive 1.0. Instead, the correlation value are either closer to positive 1.0 or negative 1.0. The various types of relationship are illustrated in the following scatter plot diagrams. The perfect positive correlation, the perfect negative correlation, and the no correlation. A perfect correlation means that 100% of the time, the variable question move together by the exact same percentage and direction. And negative correlation is a relationship between two variables in which an increase in one variable is associated with a decrease in the other. And next is the no correlation. A zero correlation indicated that there is no relationship between the variables. Various types of relationship. Some examples of interpreting correlation coefficient are followed. Coefficient R equal 0.90, R equal positive 85, R equal positive 68, R equal negative 30, R equal positive direction, negative, positive, positive, negative, positive. The strength, strong, strong, moderate, weak, very weak, inclinable. We need a statistical test to determine the correlation coefficient of two variables. In actual practice, we deal with test scores. So the data set is at interval and ratio level of measurements. To further analyze the relationship between two scores, we need a statistical test to determine the correlation coefficient of two variables. In actual practice, we deal with test scores, so the data set is at interval and ratio level of measurements. Hence, the commonly used statistical analysis is the person product moment correlation. There are different versions of the formula. The first, deviation score formula. Yan po yung formula ng deviation score. Where R is correlation coefficient, X row score in a variable X squared is mean score in the first variable, Y row score in the second variable. Next is Y mean score in the second variable. Next formula is row score formula. The row score formula is very easy because a simple scientific calculator can provide a value for x squared, y, and y squared too. This formula has been introduced earlier in the lesson 6 when you were taught on how to compute the reliability coefficient of score. This is the same person, but this time it is used to establish relationship between two sets of data. Table computation for correlation for row score data. This is the table of correlation for row score data. We have X reading, Y problem solving, X squared and Y squared and XY. In the X we have a total of 65, and in the Y is we have a total of 77, and the X squared we have a total of 517, the Y squared we have a total of 641, xy is we have the total of 548. Next is the formula. This is the formula of correlation coefficient. The mathematical process gives a correlation coefficient of 0.705 between performance score in reading and in problem solving. This coefficient indicates a moderate